Hello and welcome. Today we're going to be talking about deriving the diffusion PDE equation. And it should be noted that basically the diffusion PDE is the same thing as the heat equation, except of course a few things. One, U of x comma t is the density of particles in a domain. Okay, so again, we're going to assume there's some spatial domain X, and we can think of small particles inhabiting some one-dimensional maybe a medium which these particles can be transported through, right? And each one of these particles is undergoing some type of random motion, okay? Like so. So this random motion, they actually call Brownian motion, after a fellow who observed this while viewing pollen grains in the water. Okay, and what he saw was essentially these pollen grains sitting there just darting around, going all over the place like this. And we have to understand that I think we all recognize now that at a micro scale, there's lots of activity in the fluid, but I think that's something that maybe we didn't have a concept for always. If you were to look at a glass of water, it looks like it's a stationary thing. It looks like all the particles, the atoms consisting of all the molecules that make the water what it is, and everything dissolved in the water. We could think of it as being stationary, but in fact, of course, we know that the thing is undergoing this constant churn, do what we call thermal fluctuations. All right, and of course, if there's a particle in the water, they eventually get mixed up through this churn of particles and all this collision. All these collisions. Okay, so in order to approach this, what we're going to do is we're going to talk a little bit about some of the physical parameters underlying the diffusion equation, and we're also, of course, going to derive it. So the derivation is actually pretty straightforward. We're going to use because we're talking about a density, right? So the density is going to be maybe a mass density. Okay, so of course mass is conserved. And because mass is conserved, we can use the conservation principle. So the conservation theorem or the conservation principle applies. So what we can do is we can start off with a test set. Test set can be x in some range. We'll say a to b. Okay, and we can go as follows. So let's get a new page. We have some one-dimensional domain. Okay. And this is some sort of fluid, and we're saying that from A to B, this is going to be our test set, and we have u of x of t defined everywhere along this line, including inside of our test set. And of course, so u is going to be, it could be, for example, kilograms per meter. That could be our density. I'll use a lowercase u there. So what we're going to define now is the total mass in AB. We're going to call that capital U, AB. But I'll just simplify this to just be U of t. Okay, and that just simplifies the thing. And we can define this capital U of t in terms of little u as just being the integral from a to b of u of x comma t. This way, again, this is a function of only time. Okay. And like anything, we know so the conservation principle states that d capital U dt has to equal the flux at A minus the flux at B plus any sources. Actually, let's use a slightly different notation. We'll just say it's R of x comma t, but we're going to integrate over A to B dx. So that's going to be a source density. Okay, so we have phi A and phi B. And this, of course, is going to be our fluxes. Flux at A and B. This is, of course, very familiar with us. We've seen this many, many times. And we're going to derive it once more. And recall then, of course, that du dt, capital U dt, I can also write this in terms of a partial derivative of little u with respect to t, like that. Okay, and then, of course, we have the insight or the argument that a and b are arbitrary. So we can remove the integrals. We can remove the integrals, and we're left with this. So this is, of course, the standard continuity equation that we've seen many, many times. What we want to do now, so what I'm going to do is actually select this, and we're going to bring it to the next page. And now what I'm going to do is talk about what we're going to do with it. So again, as always, what is that flux rule? And we need a rule that's appropriate for diffusion. It turns out there is a rule for it. It's called Fick's law. And it is another negative gradient law. A negative gradient law. So Fick's law says that the phi of x comma t, we can use it as a function of time too, is going to be negative d times the partial derivative of u with respect to x. All right? It says that basically stuff or mass travels from high to low density. Okay, and we've seen this type of law in many, many, many examples before. We've seen it with Fourier's law. It's like Fourier's law, but it's in the context of diffusion. Okay, next we have to talk about D. Again, this is what they call the diffusivity parameter. So it's the diffusivity constant, and it has units meters squared over second, or just more generally, length squared over time. All right, so it turns out that there is some really important measurements, physical measurements that this comes from, and we want to talk about it in the context of Brownian motion. So what is d? How do you define it? How do you measure it? Well, there's actually two ways. There's two understandings of this. The first understanding is really straightforward, and this involves we have to look at basically tracking individual particles over a window of time. Over this window of time, what we want to do is, of course, so we can use this window of time. We're going to call that delta t. That'll be our window of time. And I want to know basically how far did a particle travel. So we're going to call that delta x, how far the particle traveled. Okay, so d, of course we're going to, what we should say though here is that we're going to perform this experiment. The experiment many times. Okay, and what we find is, of course, that d is equal to the average of delta x squared all over delta t. Of course, and that gets us our units length squared over time appropriately done. So that actually defines what d is. Okay, so what I want to talk about now is let's actually define the diffusion equation. All we have to do, of course, is plug in our partial derivative with respect to time minus the partial derivative with respect to space of the flux, which in this case is negative d partial derivative of u with respect to x, plus r, like that. And of course what we get is partial derivative of u with respect to time is equal to d, the second partial derivative of u with respect to space, plus r. Okay, cool. So this right here is the diffusion equation. Okay, so again, it's the same as heat, the heat equation, but of course the units. The units are of course different. However, it's the same structure, the same set of partial derivatives, the same set of the same sources, the same setup as before. All right. To wrap up this video, though, I also want to talk a little bit more about d. So we can imagine then that this experiment, it's hard. And in fact, because it's of course a microscopic phenomenon. It's microscopic, so in many cases it might be very difficult to do the statistics, to track all these different particles and find out where they ended up after some window of time. And so it might be a difficult experiment to run just as a practical matter. So it turns out there is another way of defining a d. So d can also be defined by Kb, so this is Boltzmann's constant, times the temperature, all over 6 pi times nu times r. So T, that's going to be kelvins. So this is for an ideal gas. So how particles diffuse in an ideal gas. Kelvin, okay. Kb, that's a physical constant. It's just a physics constant. it's the physical constant for it's related to the universal gas constant. Okay, but without getting into details with that, the next thing is going to, of course, be nu. It's this funky looking V, so it's called nu, and it is going to be the viscosity of the fluid. Okay, and R is going to be equal to the diameter of the diffusing particle. Okay, so all these put together define that the diffusivity for the thing. So of course, bigger R, less diffusive. Okay, so that of course is a relationship that would seem obvious. Larger and larger particles, they're not going to diffuse as readily as a very small particle. Okay, higher temperature, bigger diffusion. So of course particles are going to travel further if it's warmer in the fluid. Okay, and nu. Okay, viscosity is maybe a more interesting one. Of course, a greater. That's basically how thick the particle or the fluid is. So the thickness of the fluid. The thickness of the fluid, of course, if you increase, you're going to cause less diffusion. So particles will travel not as far in a thicker, more resistive fluid. So all of this thing should jive. All of these phenomena should jive with our general sense of how diffusion works. It's that things that are heavy, they can't get pushed around as much by the fluid, so they don't go as far. If the fluid is very thick, it's harder for all other things being equal, it's harder for things to travel very far. And of course, if you have a very high temperature, it means there's lots of kinetic energy, lots of molecules bashing into each other at a very high speed, causing lots of momentum transfer. And ultimately, that's going to lead to particles moving further within the fluid. So that means, of course, there's going to be more diffusion. So it turns out that this identity was really important. This is due to Einstein. And it was part of his miracle year. Miracle year papers. One of his miracle year papers, he identified this relationship through a pretty elegant little argument, and it's quite beautiful. And what's so neat about it is it details why this is such an important formula. Is that it relates macroscopic properties of the fluid to microscopic behavior of particles. And it relates them in a really interesting way. So that's why this diffusion constant formula is so useful. In later videos, we are going to go over more diffusion. We'll actually talk about cases where there's particulate matter in air, and how that particulate matter distributes and how it can disperse through the air through diffusion. And we're going to use some of these formulas. All right, thank you very much.